In this video, we discuss some preliminary results to arrive at the proof of the existence and uniqueness of Haar measures for locally compact groups. So the existence of Haar measures for locally compact group will rely on Ritz representation. Ritz representation theorem. Namely, that every linear operator that is positive on the linear operator on the space of continuous compactly supported functions is represented by the integration of a measure. So hence we look for left invariant. So let's say that we want to prove the existence of left invariant measures. So left invariant positive linear functional on the space of continuous compactly supported functions on the given group. Okay, some terminology. Okay, so G is our topological group and is assumed locally compact. Then with the C, maybe we put that 0 there, is the space of continuous functions, that are compactly supported, so such that there exists K in G compact, such that F restricted to the complementary of K is flat 0. And then on this space we consider the sup norm. So the sup norm is actually this is the maximum of the absolute value. This is in G. And since the function is like in our case is continuous, so if F is continuous, then this is equivalent to the infinite norm. Okay. Now, inside these continuous compactly supported functions, we're going to consider the ones that are positive. So by definition, this is all the functions, continuous, compactly supported, that are pointwise non-zero, non-negative, and the sup norm is positive. In other words, F is not identically 0. Okay, now we are going to consider linear operator on this basis. So for I, so it's a continuous operator on all the continuous functions. So this linear, we say that I is left left invariant if the operator on the composition between F precomposed with the left translation is equal to the operator on F. And this is for all F continuous compactly supported and for any X in G. And I recall that this is the left translation by X. Okay, then we're interested in those that are positive. So it's positive if gives a non-negative number whenever F is a function that is pointwise non-negative and different than 0. So yeah. Okay. Okay, so something that I want to emphasize is the fact that this composition is always in this space. So it's well one can calculate I. So if F is as compact support and X is continuous with compact support and X is in G, then F precomposed with Lx is also continuous because it's the composition of continuous and still has compact support, and this is actually the compact support just got translated by X or X minus 1. Okay, this is some terminology. Here are some basic properties of Haar measures. So suppose we have a locally compact group and mu is a radon measure. Then, okay, first property. So mu is left invariant and therefore is a left Haar measure. If and only if the measure mu tilde, now we'll define it, is a right Haar measure where mu tilde of a set E is mu of the set of inverse elements. So this is set of inverse elements. So all those elements in G for which the inverse is in E. And so this is a measure, this defines a measure, and one is left invariant if and only if the other one is right invariant. So this also said that there is no loss of generality in focusing on only one type of Haar measures. Second property, so mu is again a left Haar measure if and only if the operator defined by the integration of the mu is left invariant. For all X in G and for all F in C0 plus. Okay, C. So mu again is left Haar. Now we only have an implication. implies that for all U in G open and non-empty, we have that mu gives positive. So we have this implication that whenever U is open and non-empty, then the measure is strictly positive. And also we have that the integral of f, the mu, is greater than 0 for all f positive function compactly supported. So notice the strict inequality. Notice the strict inequality. And remember that we are not considering f equal to 0. Okay. Last property that I want to prove for you today. Mu, if mu is left Haar measure, then we have that the group G is compact if and only if the measure of the whole group is finite. Okay. Let's prove these 4 properties. So let's prove the first property. So we have to prove that mu is left is a left Haar measure if and only if this other measure is a right Haar measure. Okay, let's remember what's a left Haar measure. It's a radon measure that is left invariant, or maybe we want to say this. We only consider non-zero measure. Okay, so let's say that mu is a non-zero radon measure. So A means that mu is left invariant if and only if mu tilde is right invariant. Okay, so here's the proof. So the proof is just a calculation that explicitly we write explicitly what is this mu tilde. So if we now take the right translation by an element G of a set E, now by definition of the right translation, this is just all the elements E times G. Now by definition of mu tilde, this is mu of the inverse set of inverse. Now the inverse swap the elements, so this is G minus 1, E minus 1. And now we can see this as mu of the left translation by G minus 1 of the set E minus 1. Now this calculation shows exactly that if now mu is left invariant, then what we get is again mu tilde of E. On the other hand, if mu tilde is right invariant, so if this is mu tilde of E, then mu must be left invariant. Okay, so this calculation proves the first part. And of course here I'm using a lot that there is this, that every element is the inverse of its inverse. So since G goes to G minus 1 is a bijection, we have that mu tilde of RGE is equal to mu tilde of E if and not if, so this is for all G and for all E, if and only if mu of the left translation H E is equal to mu of E for all H in G and for all E Borel sets. Okay, let's prove the second part. So the second part, we start with assuming that mu is a Haar measure. So in other words, mu is left invariant, then if we take any element, any Borel set of the group, and we take any point in G, then if we integrate the characteristic of A in the mu, or we integrate x times A in the mu. See, this is, the first one is the measure of A, and the second one is the measure of x times A. But since mu is left invariant, this gives the same number. But now in the second map, we can see it as the integral of the characteristic of A composed with the left translation by x minus 1. Check that here is actually x minus 1. So in the mu. So we have this property, which means that we have the property that we want for all characteristic functions. And then by the linearity, we have it for every step function. And then, so approximating each function continuous with compact support by step functions, we get what we wanted, namely that the integral of f in the mu is equal to the integral of f composed L x minus 1 in the mu. Okay, now vice versa. Let's assume that we have this property, which is the same as saying that this operator as a function of f is left invariant. So assume that the operator that to every f associate the integral of f in the mu is left invariant. Now, the fact is, this operator determines the measure mu by this formula. Recall the formula. So for any U open set, the measure of U is equal to the supremum of the value of the operator when f is an arbitrarily continuous compactly supported function G such that is between 0 and 1, and the support of f is contained in U. So now, if I is left invariant, this sup is left invariant, right? So we get that the measure mu is left invariant on open sets. But since open sets generate the Borel sigma algebra, we get that mu is left invariant. Okay. Part C. Now we have to prove that if we have a Haar measure, then the measure of open non-empty sets is strictly positive. Okay, so let's remember that mu in particular is a Radon measure. So we have that it's regular, and mu is different than 0, right? So it means that to some set it gives non-zero value, and since mu is regular, it means we can find inside this set a positive, a compact set with positive measure. So there exists K in G compact with measure of this compact set different than 0. Okay, now we have this open set, and now what we can do, we can cover G with all the translations element So if I take xu, where x runs in K, and not in K, maybe in all of G. Okay, so to like this, right? This is a covering of the whole space. So in particular, it's a cover of G of K, and therefore we can and this is because it's non-empty. Yeah. So it's open and non-empty. So this is what we have is a cover, and since K is compact, we can find points x1, xk in G. Let's call it M, such that K is covered by the union x1 u union x m u. Okay, so now let's bound the measures. Okay, so we said that the measure of K is strictly positive, but this measure is at least is less than the measure of this union. And this measure is less than the sum of the measure of each element. Now let's use that the measure is left invariant. And we have xi, or left translation by xi. So it's u. And this is equal to m times mu of u, which means that necessarily this number has to be positive. Mu of u is strictly greater than 0. Okay, this is the end of the proof of the point, the third point. Now, no, because we were also discussing for what happens for the operator. So now, if f is a function, positive function with compact support, continuous, then we consider the set U to be all those points for which f of x is greater than 1/2 of the norm, the sup norm. Now this set is open and non-empty. Let's remember that we are not considering f equal to 0 in this space here. Okay, so then the integral of f in the mu, so this is at least, so on this set the function is greater than this quantity, so it's we can bound the integral as 1/2 of the sup norm times the measure of this set. But the set is open or empty, and we just saw it's strictly positive. So this is a strictly positive number. Now let's prove that the group is compact if and only if its measure with respect to the Haar measure is finite. So assume G compact. This is the easy case because a radon measure by definition is finite on compact sets. And therefore mu of G is finite. Okay, vice versa. So assume G non-compact. Okay, and let's fix a compact neighborhood V of 1 in G. So being compact, so the measure of V is let's call it U. Let's compare with U. U is less than infinity. Now what do? We consider again the family XU, and we know that this family, so now U is compact, this family cannot cover all of G, because otherwise, or like finitely many, when X varies of these sets, cannot cover G, otherwise G would be compact, being just a finite union of compact sets. And therefore that as soon as we fix a finite number of them, we can always find a point in G that's not in them. So iteratively, we can choose a point x m plus 1. So as soon as we fix, we fixed m points, then we can always choose one more that is not in this union. And this is, again, exists because this is a compact set and this is not a compact set. So which exists since otherwise G would be compact. Okay. Now we have these sets, and so clearly the set xiu, they might, if I fix an index I and I fix another index j, they might intersect. So these two sets, so this is xi u, xi, xju, they might intersect. Now we have to do something to make them disjoint. And we do it like this. However, using the definition of topological group, using the fact that the map, the product, and the inverse are continuous, which I can briefly write like this. I can put here -1. So since this map is continuous, then we can find set V inside G open, okay, different than empty set, such that this set is symmetric, so it coincides with the inverse elements of itself. And if I multiply two elements in this set, then they are inside U. See, this is exactly the continuity of one, like the continuity of the product at the point 1, 1. So let's fix this, and now our claim is that the family xi v goes from 1, actually these are infinitely many, these are all disjoint. Okay, let's prove it. Indeed. So if xi v intersect xj v with I different than j, then, okay, so this means that we can take elements v1 and v2 in v such that xi v1 is equal to xj v2. But then what we have that, okay, let's multiply by v1 on the right. We have xi is equal xj v2 v1 inverse. Now this is an element in xj v times v minus 1. V is symmetric, v times v is in u, and we get to a contradiction. We got that this point is inside here, but this was they were constructed in such a way that these points were not in the translations by you. This is a contradiction. Therefore, those elements are disjoint. And now then, so since V is open and non-empty, we have that the measure V is strictly positive, and hence we have that the measure of G, which is at least as the measure of the union, which now we know it's the disjoint union of xjv, this is equal to the sum of the measures of the sets. Now the measure is left invariant, this V. And now what we have, we are summing a positive number infinitely many times. And this is going to be equal to infinity. This completes the proof. Okay, I will explain you now a little bit of the idea for the existence of the Haar measures. Again, since what we saw is that there is no difference in proving the existence for left Haar measure or right Haar measure, we fix the preference for the left Haar measures. Okay, how do we do it? Okay, the final idea will be to construct an operator and use Ritz representation. But before that, let me see how one can try to think of these constructions in terms really on measures. It's going to be simpler to work with functionals instead of measures, but this is the rough idea. So for every V in G open and non-empty, what we can consider is this kind of, let's call me in quotation, rough measure. It's like this. For every Borel set G, we associate this number, which we call it E respect to V, and this by definition is the infimum of all those numbers, so characteristic of A such that A is a subset of G, so any subset, and E is covered by a union of left translations of V by elements in A. So if A is a finite number, this is the number of points, and then we translate V by these elements. So we have many elements, and if they cover E, we consider them, and then we infimize. If there is no such a finite cover, this infimum is going to be infinity. Okay, so this is how much E can be covered in terms of left translations of V. Okay, this is some kind of rough measure. And now what do we do? We should normalize, so fixing a compact neighborhood, let's call it 0 of 1 in G as normalization. We consider E going to E respect to V, E0 respect to V. Okay, so this is a normalized measure on E0. And then what we do, or what we expect to be true, that as V becomes smaller and smaller and converge to the singleton equal to the identity, then such measures, they're not really measures, but some measures converge or should converge, or maybe up to some subsequence converge to a Haar measure. Obviously, by construction, these are left invariant. Okay, so what we really have to understand is that why this converge to something. Okay, and I said this is the rough idea, but it's better to work with the functionals. So to make the idea run simple, it is better to consider integral operators. Okay, so one starts by fixing f0, and this should be similar to what we fixed before e0. And for all f, which is our e of before, and phi, which was the v of before, c plus g, we consider the operator I phi applied to f to be the ratio as before. Now we define what is the new meaning of these objects, where this ratio f with respect to phi is defined to be the infimum of all those. Now they're not just not cardinality, but they come with weights. So n is a natural number, Cj's are positive numbers, and what we have is that there exist translations x1, x, n in G, such that f is dominated by these weighted functions, the function phi, but left translated. So this is the analog of what we did before by translating the element, the set phi. Now we are translating the function, precomposing with a left translation. Okay, so this is the definition of I. And now the idea rephrased in this way. So the idea is that as now the supremum, the support of this function phi, this is the function, the measuring function, this converge to 1, then the operator I phi would converge to a positive left invariant linear functional with I on C0. Now, almost everything is clear. I mean, all of these objects are left invariant, and they are defined on the space here. What is not, or maybe is defined on C++, but then by linearity we can expect how to extend it here. What is, and they are defined positive on C++. What is really not clear is the linearity. In fact, these objects are not linear. They will become linear in the limit. Okay. But once we have this conversion to I, then, as I said before, by Ritz representation, Shell theorem. E will be represented by a Haar measure, because we proved that that I is left invariant if and only if the radon measure associated is left invariant, left measure. Okay, and we will be done. We will be done. Here, as preliminaries, are some properties of f respect to phi and the operator I phi of f. So first of all, okay, let's clarify that f respect to phi is finite. It's a finite number, okay. Indeed. So we consider the set x in G, for which phi of x is greater than 1/2 of the supernorm of phi. So since phi is non-zero, V is non-empty and open. Now the support of F is compact. Therefore, there exist elements x1, xm in G such that the support of F is contained in the left translations, the union of these left translations. Okay, now on every set xv, the function phi composed the left translation x minus 1 is greater than 1/2 norm of phi, so by definition of the set V. And moreover, we always have that f is less than the sup norm. And therefore, what we have that on xv, we have that f norm of f, which is less than 1. Now we can write this as 2 over norm of phi times norm of phi divided by 2. Now the first one, we'll leave it as it is. And the second one, we can write the function phi compose L x minus 1. Okay. Now, this is on the set xu. Now we take finitely many translations that cover all of the support of f. And then, okay, outside the support of f is not important because f is 0. Instead, on the support of f, we can bound, it was this quantity. Now, look, right, so let's move this norm on this other side. So now f is less than this on x1v, if I put x1, right? And now on each of these elements, I will do the bound, okay? So I can just sum all these bounds. And this will be a bound that is true on all of the group, on all of the support, and therefore all of the group. But now that I have this bound, what do I know about f respect to phi? Now I can take these elements as the CIs, and I have m of them. So this is bounded by m times 2 norm of f, norm of phi, which is finite. Okay, this was to prove that it's finite. Now let's also prove that it's always a positive quantity. So phi f respect to phi, I claim that it's greater than 0. Remember that f is positive and non-zero. Indeed, if f is bounded by Cj's, f compose Lxj's, then taking norms, Cj's, left translation doesn't change in the norm of phi, and so we have that the sum of the Cj's is at least norm of f, norm of phi. Now, taking the infimum, we have that f respect to phi, which is the infimum of all these sums. This is still greater than norm of f divide norm of phi, which is positive. Let's clarify that this operator is continuous, and actually even this ratio is continuous, is left invariant. Sorry, I meant to say left invariant. This operator is left invariant, and indeed, it's very easy. Okay, so if f is less than the sum of Cj's phi precomposed with Lxj's, I mean, this is true if and only if, when we precompose the function, we precompose all these other functions. And now what we can write is here that, because these are left translation, this is exactly the left translation of the product. Check this inequality, is really important. This equality. Okay, and so it's left invariant. Now, okay, another thing is, okay, it's linear, so Cf respect to phi, this is clear that this is Cf respect to phi, obvious. Now, one more property. As I said before, let's pay attention, because this is not going to be linear, but almost. So first of all, let's prove that it is sublinear. And indeed, how we do it. So say if f is less than the sum of Cj phi compose Lxj, and g is less than, okay, let's say that this is j from 1 to m, and this is from j from m plus 1 to capital M. This is just by changing g compose Lxj, then f plus g is less than this sum, j from 1 to m of Cj phi compose Lxj. And then we take the infimum, and we are done. So this quantity is definitely less than the sum of these two. Okay. Now let's check the last property, which is going to be important, maybe less obvious. What's happening if we have three functions? And I want to, so f relatively to phi is less than f relatively to another function g times g relatively to phi. Now this is why it's a little bit less clear when one considers sets, but it's better to work with functions. So now indeed, why this is true. So let's say that again, f is less than some Cj's phi, no, g compose Lxj's, and g is less than some dj phi compose Lx. Let's call this I. Xi. Then f, okay, let's start again. So it's less than Cj g compose Lxj. Now instead of g, we put, instead of G, we put this quantity. So this Cj sum over I di phi compose Lxi compose Lxj. Again, we can, let's not call it X, then be different, Y, okay? Now, again, this is left, these are left translations, so this is phi of the composition of L, Y, I, X, J. Now, now we bounded F with respect to phi with this number here. But what is this number? We can conclude by observing then the sum over J, sum over I of Cj di, this is nothing else than the sum over J of Cj times the sum over I of di, right? So what we prove is that something that bounds the first number, something that bounds the second number, as a product, bound the quantity on the left. And therefore we prove this important property. Okay. Next, we will discuss how this properties implies that the operator is almost linear, and then we will construct the Haar measure.